Hi, welcome back to our first session with the support from our supplier, Vishay. As you heard maybe just before, the zero emission mobility is becoming increasingly important, and the automotive segment is focused on, especially on fast growing market, and also the fast growing market is the electrified powertrain. The high vehicle range, as well as the fast charging time, is the main focus for electric vehicles, and that's the reason why we have a clear trend towards the high voltage semiconductors from between 800 and 1200 volts in combination with new cooling technologies. And this has a major impact in the eDrive system efficiency. But on the other side, the design is really challenging. On the other side, what we see when we go into an inverter, the DC link capacitor, for example, is and the dimension of the DC link capacitor is playing also a major role. And we know from Vishay with the product portfolio, they are covering almost all key components in the new designs of, especially of off-board chargers. Now I would like to hand over to Manuel.
Yes, good morning. Also from my side, I'm Manuel Gauss. I'm line manager for Vishay in Rutronik, and I'm pleased, very pleased that Jürgen Gewinner of Vishay is presenting some different topologies of the off-board charger for mobility during the next 30 minutes. Jürgen Gewinner is located in Selb. He is a technical field application engineer, and I'm happy to have Jürgen for this tech talk. And thanks to the audience for joining. And I wish you a good tech talk.
So hi, hello, good morning from my side.
The stage is yours.
Yeah, thank you very much, Manuel. Thank you very much, Mr. Mangler. I try to share the screen now. Let me check. Should be visible now for everybody. So also a warm welcome from my side. Good morning, everybody. Good morning, everybody. Really glad to see that there's so much interest in our session on the EV chargers. As Manuel said, I'm field application engineer located in north of Bavaria. But anyhow, if you have some kind of questions, here you see my contact details. Can you hear me? Hello, hello?
Yes.
Hello? Can everybody hear me? Okay, so perfect. Yeah, thanks. So here you can find my contact details. I guess the presentation will be shared anyhow afterwards. If not, just take a screenshot so that you can reach out to me in case of questions afterwards. I know that it's always kind of tricky to ask questions during a presentation, especially if we don't see each other properly, but so feel free to reach out even afterwards. Okay, here you can find the agenda, what we are talking about. So first of all, I want to make a short introduction and motivation about the on- and off-board charger, also about the power levels, bidirectional topologies. Why is this important? I think Rutronik has a very good market overview on that, but I can maybe add a few things as well. Secondly, we will come to a block diagram. So what is the typical, how is it typically looking like? In fact, it's not too complicated, especially not on a large view. Then we will come to the PFC stage. What are the typical topologies that we see in the market? Then to the DC to DC conversion, usually isolated. Don't worry, it will not be a lecture on power electronics, but just to have a little bit a quick overview. And finally, our main strength, it's the component level. So I think it's important to understand a little bit the topologies, the need of the customer. Why is it like this? And then we can also have the fitting product. So coming now to the first section. So what is the functionality of the DC charger? So typically when you have a look at the e-car, we have the onboard charger. So all the electronics is integrated to convert the power from the AC that is connected to the grid to the DC of the battery, communicating with the BMS system so that that the charging procedure runs well without any overcharging or short circuits and so on. But this is, according to my understanding, more an OEM business. So really the largest customers like the VWs or so in this world, and typically small power levels. So because it's just not possible to suck out more current than 16 amp out of the grid that you have at home. So coming now to the next thing, the charging power, when it's increasing to, let's say, 21 kilowatt, you typically have a wall box, therefore, and as in the previous section, as Mr. Mangler already explained, it's not the electronics which has the highest content, it's more the electromechanicals like the relays and so on. And coming now to the DC chargers, what does it mean? In a DC charger, we bypass the AC to DC conversion in the car. So that means we are connected directly to the grid. The DC charging station creates, as the name says, a DC current, which fits to the battery, communicating via the BMS and charging directly the battery. So that means all the power electronics is not in the car, but externally, which means you can save space, size, and weight in the car itself. The power levels, they differ a little bit. You can find a lot of slides, a lot of different nomenclatures and characteristics, but anyhow. So typically, the DC charger starts somewhere from 30 kV, I would say. About bi- and unidirectional charging. So very often, especially in papers or in newspapers, where people do not know anything about technique, it's very often said, all the e-cars that we have in Germany can be a perfect storage, so a distributed storage to reduce the stress on the load in case of, let's say, when no wind is blowing or when no sun is shining. So that means the idea is that you have distributed the cars all over Germany, and the power can be bidirectional transfer. That means when the sun is shining during the day, you charge your car. The battery is just is a buffer, and maybe in the evening your car is still in the parking slot and you don't need it. You can buffer back into the grid. So, but what's important here is that you need an appropriate topology. Not all the topologies, not all the circuitry can support bidirectional transfer of power. And therefore, also a little bit on it later. Honestly speaking, we don't see currently not too much requests on that. So it's usually just the one direction from the grid into the car. Okay, coming now to the block diagram. As you see here, I already explained it on the picture a little bit. So we start from the grid. We have the AC. Then here's the EV charging station, so the DC charger converting the power from AC to DC, going into the car. So this gray block here is the car, and we bypass the onboard charger and go directly to the battery. Anyhow, the communication is done with the car, so it's not just the current that is pushed into the car. There's also some sort of communication. The onboard charger, in that case, as I said, the maximum power is something like, let's say, 20 kV, usually not higher, is then bypassed. And how is the conversion looking like? So it's let's say, like in a power supply, like in a standard power supply, we have the AC. We need to have some sort of rectification and PFC, also with buffer capacitors. Then we have the DC-link capacitors, and go then to the DC to DC conversion, no matter how it looks like. and then the battery. So from a principle perspective, this is not so new. Coming now to the different topologies that we see, starting with a typical PFC circuit, or what is the PFC doing? So when you have a capacitive load, for example, it's not so. We have to have a look at the phase shift, so that phase and that current and voltage is in phase. And so we can use, for example, the conventional PFC stage, which means you can, by tuning or by driving this switch, you can have transfer just through the inductor so that you have a pure inductive load, or you can open this switch and then you have as the load as it is. So with the charging of the boost inductor. There are different topologies on the market. This is all for one phase, first of all, but I think it gives a good overview on what is available. So the conventional boost PFC stage with a bridge, with a diode bridge at the input, is pretty cheap. It's used widely, but the current has always to go through three semiconductors. So through the diode bridge, so 2 diodes here, and through one MOSFET or one boost diode. In that case, you have pretty high losses, so it's intended for pretty small power levels. When you go to a bridgeless boost PFC, like we see here, you get rid of one semiconductor, but you have a floating ground. So it's a little bit decoupled and you go up and down here, so you have higher EMI. Coming to a interleaf topology, like we see here, it's much better in terms of EMI. You can achieve higher power level, but at the end, it's a lot of components. And what I see and what we have supported already at quite some customers is the bridgeless totem pole PFC, like we see here. So in that case, you have here the 2 diodes, can also be high voltage MOSFET for the 50 Hertz rectification. And here, the actual modulation for the PFC function is done by 2 MOSFETs here, and those ones have to be gallium nitride or silicon carbide, because here it's pretty high switching frequencies, pretty high stress to the body diodes. So that's how it looked like. As I said, anyhow, if you have questions afterwards about this, you can ask. There's a 15-minute question section afterwards, and also you can contact me. So like we see here, for the conventional boost PFC, as long as we are on the positive halfway, you see how the current is flowing. So through these two diodes, positive halfway, and here either via the boost diode or via the switch. And still the same diodes. For the negative halfway, it's just vice versa. And this means, or what is nice here is, you see this inversion of the diode is just with 50 or 60 Hertz. So it's with the grid's frequency and not ultra fast. This MOSFET and this diode here needs to be, this MOSFET and this boost diode needs to be ultra fast. So low QRR, low TRR. And when we go here for 3-phase topology or for 3 phases and we play a little bit around, we come to the Vienna rectifier. So that's how it looks like. We have again here the diode bridge at the input. Here the MOSFET or the high voltage fast MOSFET, and here the boost diode. So this needs to be ultra fast, and those one is just 50 Hertz. So what we see for the Vienna rectifier is you have a pretty small volume and high power density. The stress to the components is reduced. It's not so high because nothing here is doubled. So 600, 650 volt is fine. We have high efficiency and can go to high frequencies here for the boost PFC itself. And as I said, just 600 or 650 volt MOSFETs or IGBTs are fine. And here, as I said, we need silicon carbide diodes or ultra fast silicon diode. In the last section where we are talking about the products, I will highlight the intended product. But it's just for unidirectional topologies. So there's no transfer back to the grid possible. As it's just diodes, we cannot drive them reversely or drive the current or inverted. When we want to have a bidirectional approach, there's the three-phase T-type 3-level inverter. So it's basically looking like this, here including the filtering in the input. You see it's here, it's the switches or the relays, not for high voltage, just for disconnection. You have here the LCL filter, which means filtering the high frequencies from going back into the grid. Here the shunt resistors. This is all not related to the PFC itself. The PFC is this one here. So you see here the three switches for the three phases on the high side, and here switches for the three switches for the low side. And here bidirectional switches. So how is the function basically looking like? We need to have 1200 volt devices, ultra fast, for the three high and three low side, which means you have here the current going in, here the two capacitors with a midpoint, and then from phase one, for example, current is going back from here or to here. In case that you want to have the pure inductive load, so that you switch off here and you turn on those two. And these ones is fine with 600 volt. It's not too fast, so IGBT or diode is possible, is enough. But here we need to have 1200 volt. So you can work either with ultra fast diodes that we can offer, but if you want to have the bidirectional transfer, then you need to drive those two also according to the grid voltage, like a half bridge, and then it's necessary to use silicon carbide MOSFETs. Okay, now the DC to DC conversion. For such high power levels, it is strongly recommended, and we really do not see anything else than resonant topologies. So for example, the full bridge phase shifted technology, it's isolated and it's driven resonantly. That means you have always zero current switching or zero voltage switching across the MOSFETs. It's from the setup or from the discrete components and from the passive components, it looks the same like a non-resonant switch topology. So it's really more to the IC makers that can drive the four MOSFETs in a way that you charge the capacitance, the gate source capacitance, the drain source capacitance before switching on or switching off. So the design is not too complicated. It's more the driving that is complex. And yeah, the zero voltage, so it's not important how your load condition is. It's possible to drive it like this. So you see, it's unique at the inputs side. You need the four MOSFETs. You have an inductor here as primary inductor for the phase shift itself. So this creates the phase shift, and then the transformer. And at the end, you have here the neutral point and two rectifiers. So this is one of the topologies that we see. The other one is the LLC. LLC is, I think, widely used. It's looking a little bit different. So you have the four transistors that are driving here the resonant tank. And in the resonant tank, it's not just the transformer itself, but also an inductor and a resonant capacitor that is in AC mode. So it's nice because you have always some sort of energy stored in the resonant tank. So so there's always enough power to be transferred. But as we have here a phase shift between current and voltage, because we want to have it to reduce the stress during switching across the semiconductors, we have also a little bit more of reactive power that increase the losses. But nice thing, it's a full bridge configuration, so the transformer has the full voltage in one or in the reverse direction. So which means you have less distress. Operation voltage is more or less fixed because you set this resonant tank to a certain frequency. And as the frequency is fixed, it's easy to do the EMI filtering. At the output, you have a direct bridge rectifier, for example. Now we have 10 minutes left to go through the Vishay products that we see mainly. You know that our portfolio is quite large, but the highlights and what's really new and interesting are highlighted here. So first of all, coming to the magnetics. So what we have, and these hyperlinks are also working. So when you have the presentation afterwards, you can find it. So first of all, a product that is just launched a few weeks ago is this IHCM. So inductor, high current, common mode. So it's for common mode filtering. You see it here. Basically it's like a core here. You see it. Here's the round core, and the coils are wounded here around. We flat the wires so that you can really have an SMD solution, which is reflow solvable. You can do the pick and place process, fully automatic. You have a very low profile and 155 C operating temperature. So it's really a brand new and much smaller compared to toroidal constructions and not THT any longer. So for some customers this might be interesting, especially when you have maybe a filter board that is separated from the power board or so. We have edge wound inductors. The intention to design these parts was for the LLC converter to have the phase shift with this inductor. So first of all, we can do some sort of customization here, which means if you want to have longer or shorter wires, or you want to have a hole here for connecting or for mounting these types with a bolt or with welding or so, for example, we can do so. We can bend the terminals. The construction here, these two, the coil, when it's wounded or when it's made, then afterwards, the material that we put around has the soft saturation properties, because it's the iron powder that we use in the IHLP as well. And we can go up to 180 degrees C. So it's really intended for high performance. Also, this is also possible as output filter, for example. By having no welding spots or so, it's really, as you see here, it's a fully isolated wire, and the only part that is not isolated any longer is where you do the connection, the electrical connection to the board. So we are very high here in isolation voltage, something above 500 volt. Okay, coming now to the filter capacitors. So connected to the grid is X and Y capacitors. So what we usually see, the film capacitors are mainly used as Y2 capacitors, X2 and X1 capacitors, because you know that Y2 and X2 is also possible with ceramic technology, but the capacitance value that we can achieve with film technologies is much higher. And the general trend that we see, and we also support, is to have high robustness under high humidity, which means these capacitors are tested at a temperature of 85 degrees Celsius, at a relative humidity of 85%. Oh, there was a question. Maybe we can talk about this later. Is this okay? And we apply the full AC voltage for 1,000 hours. And after these 1,000 hours, we have the measurements that there's less than 5% of tolerance of capacitance drift. So, because some customers, this is especially for the filter capacitors, this can be important, so that your filter, especially when you have this high power as we see in the DC chargers, you have to have a proper filter behavior. Otherwise, you might get disturbances back into the grid or to your semiconductors that are even more stressed. So this is done, or this is achieved by special molding technologies or special molding compounds, or by different plastic housings that is more robust against the humidity going into the capacitor. For the ceramic technologies, we have, I would say we are market leader, especially for the automotive types that are looking like this. So the single layer, so the single disc, mainly for the Y1 applications between line and phase, or line and ground, or phase and ground. So we have them in automotive qualified as well, which is for the off-board chargers not so important, but you know it's a proof of our good technical performance of our reliability. So this is the VY1 series. We have it also as compact series since a few years already on the market. What is very new and might be extremely interesting and new to you is an SMD Y1 capacitor. So this is looking like this. In principle, it's nothing else than taking this pellet, this chip or this disc, making it vertically, so it lies on the board, and on the top and on the lower side, we make the connection with a lead frame, and then we do a molding around afterwards. So it's possible to reflow solder them. It's possible to make the pick and place. We have here humidity class 2B, which means the same like before, but just 500 hours. And what is very nice is that we can also offer you a 1500 volt DC rating voltage. So that means when you have to have a filter with low capacitance value in your DC link, then you can apply those capacitors also in the DC path. Okay, so what of our main advantages is, so we are the first ones that have the 1500 volt DC rating for the Y capacitors. We have 500 volt AC, so the full voltage that you need in SMD. There is competition on the market, but here the voltage is slightly lower. We can go up to 4.7 microfarad, a nanofarad. So it's basically the same pellet that we have here. And moisture sensitivity level 2. Okay. Coming now a little bit to the semiconductor devices. So it's not always that you need ultra-fast devices. As I said, the 50 hertz steering, or in some topologies, they are just working with 50 hertz or 60 hertz. So you need single diodes that are not necessarily fast, but you want to have a low forward voltage drop. So one of the examples, for example, the 60 EPS offering 60 amp. We have the voltage range from 800, 1000 and 1200 volt, and a VF of only 1.09 volt. So in a TO247. This is, let's say, quite new chip also for us. In silicon, so no silicon carbide, as it's not fast. We have bridge rectifiers we are currently working on. So this is a preliminary picture just. It's based on the bridge rectifiers that are known since years, but we do reverse cooling. So you see the package that is on the market like this here, needed, and here we do some galving shapes. The top side will be intended for cooling, so you can directly mount the heatsink here without any isolation. So this is already isolated from the part itself. 175-degree junction temperature, isolated, and reverse cooling to the top side. Now to the FRET PG diodes, so which means fast rectifier epitaxial diode. So it's an epitaxial process. It's silicon, but from a performance perspective, it's not so far away from silicon carbide. So we have made a lot of R&D works. And here you see, for example, this is again the T-type. So you see here 3-level T-type. Here the 1200 volt ultra-fast diodes. And here the bidirectional switches. So for the input for the PFC, we recommend the 1200 volt parts. And here the phase shift full bridge. Oh no, it's LLC. It's LLC topology here for the DC to DC. And the output rectification is done with 600 or 650 volt diodes. So here you see the part numbers. and I want to explain a little bit more about these hyperfast diodes that are just released. So it's our generation 5 now. You see it here, it's 60M, here a little bit more of the values. I don't want to go into the details too much about what's written here, but I want to make some technology point. So here you see the recovery behavior of high voltage diodes, so silicon carbide, the best one. And here the shape that we have for different types. So a standard ultra fast, a very snappy or very fast one. And here you see that we do some sort of tuning, which means here we have only 1.7 volt VF. Here we have 2.1, but here the TRR and the QRR and IRR is much reduced. So it's a certain of trade-off. You can either have a very low VF combined with higher losses during recovery, or the other direction. So it's not possible to achieve both at the same time. Very important. We have silicon carbide diodes since about 1 year. So with silicon carbide, it's nice. You can do paralleling. You have a constant TRR over temperature. You have reduced switching losses. But when you have a surge current, so a very high current going into the system, you will have a much higher forward voltage drop. So this is just by nature. So what we do, we have a merged PN Schottky diodes. So there's PN structure inside as well, which make the part more robust in case of surges. We have some benchmarking, but I don't want to disclose it here. So please feel free to ask us afterwards and we can share everything with you. Coming to high voltage MOSFETs. So for the DC to DC conversion, for example, here's our current portfolio, which is expanded. What I want to highlight is the reverse 8x8 MOSFET. We have it in automotive, but it's also coming up now for high voltage. And you see here, it's just the electrical connection that is on the bottom side, and all the heat is transferred up to the top side. So there's no need for wires in the board, and the MOSFET cannot heat up the board. So maybe you have an aluminum capacitor right next to it, and you don't want that the MOSFET heats up the capacitor. For the LLC or for the phase shift and LLC converters, you need to have resonant capacitors. We have here the MKP385 series and the E. E means for e-mobility. Then we have automotive qualification as well. I need to speed up as the time is short. You get the presentation anyhow. For the thermistors, we are not the largest supplier for thermistors, you know maybe, but we are one of the most flexible about customized solution like here. So with a lock and with a higher hardness on it. So no matter if you want to have a certain connector or if you want to have different cable lengths, drilled cables, maybe colors that need to be different, or one connector with several NTCs connected there. So we have a very, very high win rate here. When it's about customization, we are here really flexible. For the shunts, we have not just the power metal strip, but in that case, it's only the power metal strip that makes sense for the high current that we have. So here's SMD Solutions, but also a screw terminal solution like the WSBS. The D-sealing capacitors, we have made a lot of experience since the last 10, 15 years that we are on the market with the MKP 1848. We are expanding the portfolio to have higher robustness against humidity. We have automotive, slim versions. We have compact versions. This is just data sheet stuff, but what is important and what is not visible at the first sight, we qualify our parts at 85 degrees C. So that means a 700 volt capacitor from Vishay is an 800 volt capacitor from competition. So because competition or some of our competitors rate their caps at 70 degrees C. So it's different approach. So when you're looking for 800 volt device, you need, in fact, from competition, you can use a 700 volt Vishay part as we rated at higher temperature. This is something that is not visible at the first sight. Same with the ripple current capability. The last product I want to show, then we are just 5 minutes over time, is for the passive cooling and isolated heat transfer, our new THJP. So it's a thermal jumper. You see here how the construction look like. It's in principle, it's a piece of ceramic, like in a chip resistor. We do a termination around, a bob around, which is just there to be soldered and to mount this type on the board. And the trick, or what is the intention we have, you have here, you see a resistor driven at a certain current with a certain amount of losses, so that the temperature is about 150 degrees C. Then we place this chip right next to it, our thermal jumper, which is then connected from here to here. So then you see it with the thermal image, it's not visible so good, but when it's explained, you can see it. And then the heat is taken via this resistor or via this jumper to a larger plate, for example. So that the temperature at the end is more than 50 degrees C reduced, which means you have either less stress to this resistor or can drive it with even higher power, because it's the film temperature usually that limits the maximum power. And when you see it here, we have different versions, also in flipped, so like 0612. And looking at the thermal resistance, so we are here, the lowest that we can offer is 4 Kelvin per watt. So it's really tremendous how much power you can suck out from the board, or how much heat you can suck out from this board, and maybe use less semiconductors here or drive them at a cooler temperature. And it's isolated, electrically isolated with more than 1.5 kV. That's it from my side. I hope you enjoyed. If you have questions, please feel free to ask. And I thought there was something coming. I have to check.
Yeah, thank you very much, Jürgen, for this great presentation. And we learned, the key components are not only the semis and especially this idea with the thermal jumper. Never seen it before. It's a cool idea. To get rid of these of the heat, especially around the shunts and so on, or whatever you have on board. We are just running out of time a little bit, but I would like to hand over to Manuel regarding the first questions in our Q&A session.
Yes, thanks also from my side to Jürgen. One question is coming regarding the silicon carbide diodes. How does the Vishay roadmap for silicon carbide diodes look like?
Okay, thank you. It's a good question. It's a really interesting part. Yes, in fact, currently our silicon carbide MOSFETs offer 650 volt breakdown voltage. So here you see the current portfolio, 650 volt in TO220 and in TO247 with 3 leads, just also with 650 volt. And by next year, we will come up with 1200 volt, and we will also come up in D square pack and D pack, so SMD packages. This will come by next year, and partly this year.
Okay.
Any more questions?
Yes, one further question. The question was, I know that Vishay is producing power modules. It's possible that you integrate diodes and MOSFET and IGBTs to provide a customized and application-specific solution. Is it possible for you?
Yes. In fact, when you look at the topologies, so like here for the a module that has the 4 MOSFETs, for example, integrated, or like here for the T-type that you have several diodes and MOSFETs integrated, yes, we can do so. So we have some standard solutions, especially in the EMI pack module, but we can also do, on request, have a look at if there's a customized solution possible. it depends, as always, on the quantities and on the amount of development and what is actually needed. But in principle, yes, we can do so.
Okay, thanks for your answer.
So we are just running a little bit out of time. Yeah, but there are so far no further questions from the audience. But please feel free to send us further questions via eventadmin@rutronik.com or direct to Manuel, manuel.gauss@rutronik.com. Yeah, feel free to contact us. As Jürgen mentioned, the slides will be available for download for all the participants, and we will give you then the link for the download. So Jürgen, thanks a lot. Thanks for these good inputs. And I think you showed very well that there are so much things need to be considered in the inverter design or in the charger design. And we also found out, of course, that and we at Rutronik knows that Vishay has the broadest range in components for the charger designs. And thanks a lot.
Thank you
for your presentation.
Thank you very much. Have a good day, everybody, and enjoy. So, yeah, good success with your designs, and hopefully with Vishay components together with Rutronik.
See you soon, Jürgen.
See you.